Okay, great. So as usual, um, we'll do the same thing as usual. We'll go through each section, and after going through each section, I'll probably go through some examples, and I'll be open for anything. Right? Stop me at any time. Open your mic. Stop me at any time when you want to ask questions. When you have specific things you are not you don't really understand yet, and we can discuss, right? We can talk about it, you know. Yep. So that's that. Let's begin. So okay, chapter 4. So this is what we're going to cover this week. Um, okay, let's start from 4.1, commutative groups. Anyone have any problems with this section? I'm gonna go faster. So finite groups. Nope. Generators. Nope. Wait, let me turn on my message just so I can see if there's anyone in the chat as well. Okay, great. So finite groups, generators, exponential map. Any questions? Factor groups? No. Pairings? Wow, okay. Oh, exponential map. Okay. Okay. So great. What questions do you have on the exponential map? If you don't mind sharing. Okay. Then let's look at exponential map and see if it helps, right? Okay. So, first of all, to add some context, I might as well, since we're here, I'm gonna go through a little bit on groups, finite groups, and all that. So, groups, think about it as a set, right? It's a set with some operations. So, that's why you can see, of course, it has some property like commutative associativity, but what it means is essentially you can do it follows the rule of arithmetic, some of the rule of arithmetic, like addition, a plus b is equals to b plus a. It's similar to that. So yeah, there is a neutral element, which is the identity usually. So one or zero, depending on if it's a multiplicative group or a additive group. And yeah, there's an inverse, right? An inverse, in this case, -1 for an additive group, and you know, uh, power of -1 for a multiplicative group, right? So there's this existence of inverse. So usually when we talk about groups, we do talk about commutative groups, and we sum all these properties in there. And groups usually, yeah, we represent it like this, right? If it's additive, it's this. If it's multiplicative, it's here. Okay. And the difference is essentially the operation. So we define group as a set with some operation, with one operation, right? Usually one operation. So in this case, it's G and addition. In this case, it's G and multiplication, right? And yeah, that's what a group is. Finite groups, finite amount of things, right? Infinite group can be integer with addition, right? Because you can have integer that adds up to an infinite. Finite group usually will work with some finite amount of numbers. So Z6 here is just natural number up to 6. So 1, 2, 3, 4, 5, 6, essentially. A set that contains these 6 numbers, so to say. Yeah. And yeah, that's essentially yeah, can be commutative mod 6. You're right. Yes. So that's essentially what finite groups are. And generators are just a value or element in such groups that you can use to generate other elements. Um, we usually will be more interested in groups that have a element that can generate every other single element. Um, so that's pretty interesting. That's the interesting thing we usually look for, right? With one generator that generates every other element in the group. Yeah, but again, a group can have multiple generators. No, generator doesn't need to be a prime. In fact, even in non-prime sets, so non-prime groups, you can have generators as well. It doesn't need to be a prime. Um, it's just that, um, how do I put this? It's just that sometimes some generator, I believe we do use prime generators in some cases, but generally what we want is a generator that gives us certain properties. That's why in practical applications, like for example, our famous SECP256K1, we choose a specific generator point, right? And then we use that point to generate the rest of essentially the field yeah that we use. But no, it doesn't need to be prime number. Generators, that is. Yeah. But we do we do like groups that have a generator that generates all other elements in the group. Yes, ZK, you're right. Some elements are able to generate all the other elements in the group, but not all, right? Some generator only generate three or four, right? A very good example is in the group of in an additive group of, let's say, integer. Technically speaking, two is a generator. You can generate every other, not every other number. You can generate a lot of numbers. Like you can generate 2, 4, 6, 8, and so on. But it's not the generator generates all the other elements in the group, right? I would say one is probably in this case the generator that's able to generate all other elements in an integer, or I would say natural number. Integer. Yeah, natural number. No, I'm not sure. Wait, natural number. Yeah, generate all the other natural number because you can just one plus one, one plus two. Then if you continue to plus one, in this case, you are able to generate every single number in the natural number group. So yeah, that's what a generator is. Generator doesn't need to be prime number in this case. Generator is just a number that you can use to generate other numbers. Yeah, great. So yeah, that's that. So let's go into the question. So exponential map. So exponential map here is just that it's essentially a mapping that maps a group. In this case, they're using additive group. So an additive group to another group in this case. So here we are basically saying, hey, so let's take the example here is Zn plus. So this is an additive group of integer that is of size order n, so size of n. And yeah, we want to map this to another group, and we want to make sure this mapping is one-to-one, right? So exponential map because it operates as in exponential of gx. So this G is not a predefined set. In this case, it's like basically we want some mapping. In this case, this is the mapping, and we want to map values in Zn to another group, right? It essentially creates a new group. So yeah. And when we do this, we want this to have a one-to-one correspondence, meaning that we don't want values from Zn when we do this mapping to two values to map to a single non-unique value, right? So we want every mapping to be unique. So that's essentially what the exponential map is. To put it very simply, I'm gonna go through here. So to put it very, very simply, this is an example. Okay, we'll use this example. So this is discrete log to the base of 3, and this is the map, right? So wait, this one, let me see. Oh, you can repeat the experiment. Results 4. No, this is not a good example. Wait, let's take this. Yeah, this. So this essentially says we take this map of this is additive, I believe. Yeah, this additive group that maps to this multiplicative group of order 5. This is order 4. And this is the mapping, right? Do 3 to the power x. And one thing that we need to essentially um, be aware of is we want it to respect essentially the law for each group. So what do I mean the law? Basically the operations, right? Group for 5 doesn't contain zero. Yes, a multiplicative group of 5 doesn't contain, so you're right. This is because actually in all multiplicative group, um so zero, it's interesting in that sometimes you can't, well, we don't necessarily generate zero out of this mapping. Um it's more towards, so zero in some definition we'll say, like, let's say additive group, right? We want a, because remember this actually is because of this definition here, um existence of a neutral element. So the set that you are defining, sometimes we'll say like, hey, we specifically define this set, and then we'll say, hey, there is a identity, or there's a neutral element, and this neutral element is zero. In the sense that any value plus this value is equals to zero, or and so on, right? Like the inverse of this value times this value is zero. It's like some neutral element, right? And yeah, that sometimes we define it, but sometimes you can't really, at least from my understanding, it doesn't necessarily mean that it exists naturally in the set. You can define a value such that you define basically, hey, this is the neutral element, and we do this, right? But you need to respect, of course, like, that element times you get the inverse, multiply the inverse by itself, and you should get that neutral element. In additive, very commonly it will be zero. In multiplicative, very commonly that will be one. So multiplicative group, sometimes it doesn't, I mean, it doesn't necessarily have zero. The zero of a multiplicative group usually we define it as one. It depends on how the group is defined. Yes. I'm not sure if I make sense. I might not be describing this very accurately. Anyways, yeah. So let's get back to here. Where were I? Okay. So in this case, so this example, um, this essentially is calculating for the mapping from X. So like, let's say, I think this given this X is sure in exponent generated 3, so this is a generator, and you basically do this computation here and you get 4, right? And this value, excuse me, this value should respect it should respect the law also in this, right? Basically, anything you perform in act like in Z4, when after you do this exponential map, um, the values here, or more like, how do I put this? So 1 plus 3 point plus 2 in this group, for example, 1 plus 3 plus 2 is equals to 4, 7, 4, 5, 6. 6, which goes back to 2, I believe. In this, I believe, yes. And in this specific case, 2 here, if you map to Z5, should always be 4, essentially, right? Yeah, so let's read this a bit. So in this, we perform this in a remainder class group here, and then apply this map. But we can technically do the same thing in this group, and then it will result in essentially the same value. Because basically your computation works, your computation should translate well. Like you should respect what will happen in the group that it's coming from. So any computation performed in Z4 when mapping to this should be the same as if you perform a computation here in Z5, multiplying the group of C5. Yeah, that's essentially what an exponential map is, but specifically we are talking about exponential. So like g to the power of x. Z4 and Z5 isomorphic, they have the same order and they are cyclic generator. Yes, I believe so. Yeah. Gerald, does that like answer your question in this case? Nice. Great. I think there's one more question somewhere. In exponential, how active group with group order 4 maps to multiplicity group of group order 5? Oh yeah, I think that's answered by NH Shah. Base G discrete. Oh, are you talking about base G discrete log? Wait. Base G. Oh. Since the explanations one correspond to respect the group log, can show that this might have an inverse with respect to base G. This one. Okay, 4.1. What is it talking about? Where's 4.1? So this is essentially base G discrete log is this, right? This is the reverse. So if there is a one-to-one correspondence, if this is a like if there's a one-to-one correspondence of Z to G, Zn to G in this case, right? If this is true, can say that if this is true, the reverse, the inverse of it, is true as well. So this is essentially a reverse, right? Can we put the set aside? Damn it, I need to install something else. So this is essentially an inverse of this, right? So that's it. That's what it is. So log gx essentially just shows a mapping from G to Zn instead of the previous way it shows Zn to G, where Zn, the mapping of Gn to Z is in this case G to the power of x, right? And G is a generator. So for example, the inverse of this would be, yes, it's hard to compute the x from result, discrete log. At least that's what it wants to do. And it's the thing that we rely on to make sure our cryptography is still relatively safe. Yeah, that's the discrete log. But yeah, for example, this the so in this case, let me see if I can get the pen. So in this case, the inverse should be Z5 mapping to Z4. Sorry, my handwriting is crap. And then this will be base 3, so log 3 x. Yeah, so this would be its inverse, right? This is the inverse. Yeah. Okay, great. Any more questions before we move on? 2 to 4 in example 4.3, 4.4, 8.3. 4.2. Oh, this 2 to 4. Yeah. I mean, if you don't know 2, it's harder to know it's 4 in here, right? Um, yeah. Or I mean, from 4, you can't really know what's 2. Yeah, in the opposite way. I would assume there's no questions, so let's move on to. Oh, there you go. Solidify is a mapping because it's both injective and surjective. When A is not equals to B, FA is not equals to FB. And for every B, there is an A that maps to it. Yes. You can confirm this. Yeah, wait, it's checking by hand. Yeah. Yep. Yep. Bing. Yeah, Bing, you're right. Thank you for the additional context to this. Helps a lot. By the way, guys, remember there's a chat. You can look at the chat. There's a lot of discussion going on there. So do take a look at it. While I'm also talking. You can also talk, by the way. But yeah, thanks, Bing, for the more accurate explanation, I would say. Yep, great. Let's continue. So, factor group. Any questions on this section? Okay, let's go into pairings. Any questions on pairings? Oh, okay. Great. Wait, this is under pairings, right? Oh, this is after pairings. Okay. Any question on cryptographic groups? So in cryptographic groups, we talk about DLPs and a few things that modern cryptography rely on, and some assumptions to make sure that things are essentially safe. We also talk about here. So here we actually talk about H equals G to the power of X. Yeah, it's essentially given this. It's pretty hard to find H without knowing X. Essentially, finding the inverse is hard. That's what DLP is. To be very, I mean, I'm explaining this in a very simple way. So it's, yeah. Okay, I see a question. What is non-degenerates in pairing? Pairing is non-degenerates. Okay. So um essentially, let's talk about pairing a little bit. So pairings, or pairing map, essentially, it's so a pairing map is this function. So G1 times G2 maps to a group tree, right? One group maps to another group. Sorry, one group operates with another group and then maps to group tree, right? In this case. So and pairing map, so it maps it and it makes sure that this property called bilinearity holds, which means that essentially, if you do this, okay, this identity, okay, so G1 um times G1 prime and G2. So this pairing check, it's equivalent to this, right? So it's equivalent to operating. Okay, to put it very simply, doing this operation or doing this operation is equivalent to doing the calculation in these two groups is equivalent to doing the operation or the calculation, the computation in G3, which is the result of this function, right? This mapping, so to say. So yeah, this is explaining a little bit better here. So bidimensional means that it doesn't really matter if you execute the group law on one side that appear the binary map, or we first apply the map and then apply the group law. Group law here is the operation itself. So the operation it like addition, multiplication, it depends, right? It depends how you define the operation as per groups, right, in a group. But yeah, usually multiplication, addition, yeah, that's what it is. So it doesn't matter if you do the calculation here first or you do the calculation here. This should map to this. And let's now talk about non-degeneration. So non-degeneration means that okay, remember in groups when we talk about a neutral element, it's very likely the identity element, I guess. So essentially, a neutral element for an additive group is, for example, a neutral element for an additive group will be zero. A neutral element for a multiplicative group is very usually one. Neutral element here just means that, hey, if it's an additive group, 0 plus whatever, it's equals to that value. So 0 plus 5 is 5. And for multiplicative group is 1. So it's 5 times 1 will always equals 5. 6 times 1 is equals to 6. And so on, right? So non-direct just means that if if the result in G3 or the result of the mapping is a neutral element, let's say if it's 1 or 0, in this like inside, yeah, so if 1 or 0, right? Then one of the input value in G1 or G2 must be that neutral element. And yeah, so I think we can look at the example here. So the most basic example involves this and percentage addition. So this essentially is so this mapping is a times b on integer. And so this is non-degenerate because given, let's say, okay, equation a plus b times c, so to say, this holds, this is binarity, and then it's non-degenerate because let's say this is 0, then it means a or b must be 0 in this case, right? If a times b is not, it's 0, but a or b is, sorry, if a times b is 0 and a or b is not 0, um, then it's not non-degenerate, and it also imply, I think that's some problem with my, sorry, give me a moment. Okay, great. There's also imply that there is a, well, I guess in this case there is a inverse of a value, not inverse actually, yeah, I guess, yeah, so I guess so there's an inverse of a value in G2, right? Yeah. So yeah, this is what, generally non-degenerate just mean that, hey, given that the pairing result of pairing is 0, one of the values should be 0. If it's not, then it's not non-degenerate, and that's calculating it. Like when you calculate things here, it might not necessarily map to the correct value here. So unless A or B is a natural pairing, result should not be a neutral element. Yes, unless one of them is a neutral element. Yes. But this is the non-degenerate property, right? You can have a pairing map that is degenerate. Okay, that's a little bit fun. Okay, anyways, yeah, you can have a pairing map that is degenerate. Um, but this is a nice property to have. I believe. Yeah. Great. So let's continue. Any question, just throw it out. We can go back to it anyways. Yep. So cryptography group. I might as well, since we're already here, let's talk a little bit about this. Yeah. So here, the result. I'm not. The result can be unique and not accidentally equal to neutral element and thus making false validation. Um, I am not. Yeah, I mean, I'm not exactly sure if that statement is right. The result can be unique and not accidentally equal neutral element and thus making false validation. So yeah, I'm not exactly sure about this. So if any one of you have any insights in this, yeah, do participate. But yeah, I am not sure it exactly means that. But on the yeah, it not be the chicken pairing of results, C should be C and not E. Yeah, I mean in that case, I suppose so. So it's a unique result, but I'm not. So what I'm not sure about, if I'm not that what I'm not sure about, it's essentially, um, yes, you are right in that, but I'm not sure if that's the only reason why non-degeneracy is a good thing. Um, yeah, I am. So what I'm not sure about, if that's the exact so that's I'm not sure if that's the only reason why non-degeneracy is a good property to have. But yeah, I mean, you might be right here. This one I'm not very sure. Yes. Okay, so cryptographic groups. Here we are talking about groups that we'll usually use in cryptography essentially. But yeah, they talk about discrete log problem. Yeah, so let G be a finite cycle group of ordered R and G be a generator of G. We know there's an exponential map that maps residual classes from modular R arithmetic onto group 1 to 1, and discrete log problem is the task of finding an inverse to this map. Um, yeah, to find solution X R to the following equation for some given HG, which is an element for a group. So yeah, um, there are groups in which this is assumed to be infeasible, meaning it will take more than the time in the atoms of the universe, some of them, to solve. And there are groups in which isn't. So we are interested in DL secure groups. Um, yeah. So in public key cryptography, this is quite a common thing. Encryption, I believe, just symmetric is asymmetric encryption. I mean, but I think both does use this. But yeah, it's used in normal encryption, decryption as well. So yeah, here in this case, secret key is some SK. So this is quite common. Um, Need to find the result for this equation, and it's pretty hard to find it. Yep. So there's also the decisional Diffie-Hellman assumption. So this is definition. So let's G be a finite cyclic group of order n and let G be generative G. The decisional DDH problem is to distinguish GAGB, GAB from the triple GABC for uniformly random values ABC that is an element of the integer set of order R. Um, yep. So these are all things that ensure our cryptography protocol remains secure. And there's also this Diffie-Hellman assumption or competition. Diffie-Hellman is some yeah. So I'm not gonna what's it called? Read this out. Yeah. Any questions? What's the difference between decisional and computational DH? Very good questions. Okay, so let's look at let's look at the definition. So this is problem is distinguish this from the triple this. And if you look at here, this given a randomly integral chosen AB of this, it's not possible to compute GAB if only GGA and GB, but not A and B are known. It's slightly different in that how do I do this? Okay, from my understanding, given this, so given this, and some random value ABC, without this is triple, right? Wait, let me think for a little bit. Need to look at my notes. So DDH is stronger than it's stronger assumption than CDH actually. Um so it's actually a stronger assumption than so DDH is actually a stronger assumption than CDH, and the difference is essentially given this determining if C so this C is necessarily equals to A times B um is hard, or more like if you want to look at, like, let's say GC, you want to determine if GC is equals to G to the power of A times B, it should be hard for you to do so in this case. Yeah, but yeah. So, however, so if you look at pairings, so at least groups that you can efficiently compute pairings, you realize that pairings are not DDH secure in the sense that given some GAGB, you can check if GAB is equals to GC in this case by doing a pairing check. Because of bilinear property implying this. Yeah, so technically, at least from my understanding, in pairing friendly's curve, or more like pairing friendly curves are not really DDH secure. However, I believe they are CDH secure, in the sense that computing. So here is essentially okay. Let me see what I can. Okay, so essentially, so this you can compute this, right? But computing GAB, so you can check the pairing. You can definitely check pairings of you can definitely check pairings between of to do this pairing check to actually get the relationship of GA, GP, and some value Z, which might be GAB, right? But in this case, although yes, you can, but in here, it's considered acceptable with CDH assumption. So is it correct that DDH is check yes, no, and CDH is a search problem? Knowing GAGB, compute GAB. Uh, oh, and CDH is a search problem. Let me think about that question. Is it correct that DDH is check yes, no, and CDH is a search problem? Known GA and GV, compute GAB. No, you can compute GAP in this case. Wait, no, you cannot, yeah. Is it, I'm not sure if I would call it a search problem. But yes, given GA and GP, compute GAB is hard in CDH assumption. Comparing two is an upper is computing from some value pairing groups is feasible because pairing can help check the correlation and we want it to be hard in DDH. Yeah. So yep, ZK is giving ZK I think, and also MHA is also giving really good feedback in the chat. So yeah, pairing groups, it's DDH infeasible because pairing can help check the comparison where we want it to be hard in DDH. So well, I guess in CDH, it's not this hard of an assumption. So ZK also gave an example. For example, we want Z equals G to the power of AB, but we don't want people to know Z equals G to the power of AB. So in this case, you can find that out via a pairing check.
Can I add something here?
Sure, go ahead.
So I think the question on computational and the question on search problem and whether it's check yes or no, I think that's somewhat accurate, I think.
Mm-hmm.
Because, okay, it's on your screen right now. Like if you read the paragraph to see why the descript log assumption is necessary, blah, blah, blah.
Mm-hmm.
Um, at the end of that paragraph, sorry, it's the paragraph below. So given
Oh, okay, okay, okay.
a g to the power of AB, you can decide
Mm-hmm.
if the DTH assumption holds, but then it's hard to compute g to the AB.
Mm-hmm.
And then in this case, the weaker assumption means that it is better because there's less assumptions.
It is okay.
Or rather,
Thank you.
stronger.
Yeah, strong. You mean stronger than the what's it called? DL
Yeah, than the
assumptions?
decisional one. Because the decisional problem, you're just checking, right? You're just checking if
Okay.
some z equals to g to the AB.
Yes.
But then the combinational problem is trying to ask you to compute g to the AB.
Ah, I see. Thank you very much for the context. It helps. Okay. I guess any more questions from the audience or any more context that you would like to add to this? Then I'll continue. I suppose. Again, thank you very much for adding to this. Yeah, it helps me as well. Okay, so next, hashing to groups. Anyone have any questions regarding this? Hashing to groups. Any questions? Hash functions. Hashing to cyclic groups. Peterson hashes. Pseudo-random function families in DH secure groups. Okay, then we move on to commutative rings. Okay, hashing into modular arithmetic. Anyone actually tried this in Sage? Maybe we can try it later together on like my laptop. But yeah. Hey. Oh, I think there's still conversation on DDH. This means that there are group and DDH on DDH don't know there cannot be groups in which DDH holds but CDH doesn't hold. Essentially, yes, CDH is better than DDH in strength. Yeah. Um I guess the so in the book, okay, let's go back to the CDH and DDH. So ZK was talking about, I think DDH is kind of depending on CDH two does that statement, like pairing is one. So and then being replying, this means that there are groups where CDH holds and DDH does not hold. Well, they cannot be groups in which DDH holds, but CDH does not hold. Essentially, yes, CDH is better than DDH in terms of strength, but I found this sentence really phrased in the book. Mm, yeah, I think the book because the book talks about the CDH assumption being weaker than DDH. I guess that's why it feels weird. In that sense, I guess they are talking about it's a weaker assumption, but not necessarily a weaker assumption in that it accepts more. I think that's the reason why they say it's weaker. Not exactly that. Yeah, I think that's why the book phrased it like that. So it's weaker in the sense that DDH accepts less. Like the DDH assumption accepts less. Like that there are higher. Yeah, I think not higher. They are DDH is more strict than CDH in that sense. It's weaker in the assumption front, not in the. Yeah, not in the. I mean, I don't know how to put it. It's talking about the assumption strength, not the strength of. Yeah, because DDH if DDH holds, CDH must hold. But if CDH holds, DDH does not necessarily hold. Yeah. Reduction could be if we break CDH, we can compute J. If we and compare it Z plus J and plus DH. Isn't it? Okay. Yes, I think Cha is right. If we break CDH, we can technically break TDH. Because we can find Z equals G to power AB. To check G to the power of A, B equals G to A plus and G to B in pairing, it has to be easily compute GAB from GA to GB. Yes, that's right. What? Oh, weaker assumption, you assume less. Yes. Uh, break harder problems, you can break the easy problem with some assumption. Yes, you're right. So if you assume, if you basically use the bigger assumption because the problem is hard. Yes, you're right. Bing, in that sense, yes. Thank you, Bing. Great. I'm so happy. There's so many discussion here. Okay, great. Okay, let's get to Rafina. What does non-unique mean in example 55? Where's 55? Unique. Okay. Oh God. Yeah, the search is not great. 55, page 54. Wait, 55, page 54. Let's get here. Sorry, a moment. Wait, 54, example 55. Where is it? Hmm. Oh. Uh, Honestly, I do not know. This I actually don't know. I think this is a printing error, but I might be very wrong about this. But yeah, I have a feeling this is a printing error because I think I saw similar things up in pairings as well. I think this is marked for removal or it's basically saying that the example is not unique. I'm not very sure. Yeah, correct me if I'm wrong. Yeah, I'm not quite sure why this is written non-unique. Sorry. Yeah. Okay. Yeah, hashing into um okay. Commutative rings. Any questions on commutative rings? Well, this is like a bunch of symbols. Okay. Hashing into modular arithmetic. Any questions? I'm gonna slowly scroll down. Try an increment method. Anyone tried to implement this? Actually, it's fine. Let's continue. Okay, fields. Um, any questions about fields? We usually one note here, so we usually actually use prime fields in most of the cases, in cryptography at least, due to the fact that there are quite a lot of well, not quite a lot. There are properties that we want in prime fields or in prime, yeah, fields with prime order. Um, and that's why prime fields are quite commonly used. Um, yep. So let's continue. Square roots of fields. Any questions? Yeah, do just put it in the chat or stop me when you have questions or you want to discuss about something. Hashing into prime fields. This is the same as hashing into groups, actually. Actually, most hashing into prime fields, hashing into modular arithmetic, and hashing into groups. They all use the same mechanism as hashing into groups. Prime field extensions. No. Okay, finally, projective planes. Any questions? I'll wait for a little bit more for any questions before we kind of do like a conclusion of everything and ask for any discussion points. Anything? If not, then let's quickly go through each part. I guess no questions. Or what is funnel plane? I might be very wrong with this, by the way. Funnel plane. So it's a name for projecting plane over finite field F2. We can actually try to compute this, I think, with Sage. They don't have an example code for this, so it might be a little bit hard for me to compute this. But yeah, funnel plane is, I believe, just the projective plane over finite field of F2. So this is the projective plane over F3. No, this is the associative one, I think. Uh, is it? Yeah. So yeah, final plane is just a projective plane over F2 instead of, well, F3. Any more questions? So let's quickly talk about rings. We talk about groups. Groups essentially a set of values with an operation or with a group law. Rings is a set of um or more like two groups, essentially two groups, because but the two groups usually will be on the same set, and essentially it's a combination of two groups with different group laws. Very commonly additive and multiplicative. I think here, yeah, so here it talks about commutative rings with units, and it's essentially a set with two maps, addition and multiplication, and using one as the unit, such that these properties hold. Um, so yeah, that's a ring. So a ring essentially, yeah, sets with a tuple. I mean, it's not a tuple, it's a triple in this point. Containing a set and two operation. Actually, in this case, it includes a unit. So in this case, the unit is one. Ring is just a group that has two operation. Ring is you can call it not a group with two. So a group is a set with an operation or with a group law. A ring is a set with two operations, or more like a set with, or two groups with a unit in this case. Yeah. It's not, yeah, it's not really just a group that has two operations, but yeah, it's a set with two operations, kind of, yes. Yeah. I'm describing it like in a very simple, non-formal way. So yes. Um, and we can actually jump to field. Field is essentially a ring, but we want additional properties, which we have this neutral element 0 and a neutral element of 1 for multiplicative group, and there is an inverse. So there exists, how to put this? Every non-zero element must have an inverse. So that's one of the extra properties that fields have. Um, Specifically multiplicative inverse, not additive inverse. Um, yeah. So fields are essentially just ring with extra rule, to put it in a very simple term, with extra conditions or extra properties that we want. Yeah, so that's fields, and we will usually use prime fields. In this case, we define square root, and in situation where, I mean, when we operate with sets or values or groups that don't really, yeah, I think I need to rephrase that better. When we operate with fields, square root, it's so because we work with integer, usually we, in a sense, ignore square root that gives us real numbers. In this case, right, in this specific context, of course, if we are working with real numbers, real number fields, that's not the case, right? But in this case, we take anything that we can beautifully square root. So if x equals square to y, and y, the square root of y would be x, right? And we call y essentially the quadratic residue. if y is given and there's no solution x, so if we cannot square root y, then y is the quadratic non-residue. This is just terms that we are going to talk about later in the book. So yeah. And this is essentially a way of describing if y is a quadratic residue. Yeah, I'm gonna go here. So prime field extension. So prime field extension essentially is a way for us to extend on certain prime fields, and this is very useful when we need. And I'm putting this not very accurately, I believe, when we need more points essentially in a field. When we want to do, and this is very helpful. Again, do correct me if I'm wrong, especially for those that might be able to explain a little bit nicer. In some cases, we do extensions on prime fields because we might want to do some calculations that needs those extra points. That's one. That's one of the examples that we need prime field extensions. And you can usually do an extension like so. I mean, well, you need to redefine how addition is done. But essentially, addition is done quite straightforward. However, multiplication is slightly more difficult because it involves choosing a polynomial p. In specifically a irreducible polynomial means that it's a polynomial that cannot be further factorized, and then using that as essentially the mod, right? Yeah. So that's essentially what we call a prime field extension. You attempt to extend your original field with additional points, and when you extend it, sorry, it's basically on polynomials that contain no roots. Yes, it adds polynomial that contain no roots. Or yeah, non-factor, yeah, not reducible, yes. And this basically gives it more point. If you use, I think down below, yeah, this shows you how it's done. So it's essentially it added more polynomials, right? It extended it to have more polynomials in this case. Again, you need to choose a polynomial, irreducible polynomial, and you put it in, and you get this. And if you use, so this is the entire table for multiplication. You can compute it by hand, by the way, to extend it. But if you use Sage, you can actually do it quite easily. If you use a programming language, you can usually do it. But yeah, that's essentially what we call a prime field extension, usually on the prime field, yes. And so finally, projective planes. So let's quickly go through this. So projective planes, how do I put this? I can't really say it adds another dimension, but it is technically doing that. So it, okay, essentially it wants to add a point at infinity so that we can represent it. We can represent elliptic curves easier and do some computation. That's the point of projective planes. You can think about it as, I don't think it's very accurate, but you can think about it as adding a axis from 2D to 3D. It's not really that. You can think about it like that. And we want, so this describes it quite nicely. So we want, given this field, right, we want to create a project field, and you want this property of kx times ky times kz. K is a subset of the field, but this, so any k here is equivalent to actually xyz. How do I put this? I think this is pretty hard to explain. So technically these two are equivalent. They are equal to this when we extend it. That's the property of projective planes in this case. That this is this is weird to explain. Yes, this is equivalent to 0, 1, 1 because of k. This is a little bit weird for me, but I believe this is correct because of the k. Let me see. Yeah. So let me see if I can explain a little bit. Let me formulate my words. It's well, let's see. Through so in elliptic curves it's just basically a way of defining some points in elliptic curve where the graph actually extends into infinity, and this adds the point back. So it kind of says include points at infinity, and for parallel lines or for lines that will never intersect in a normal Euclidean 2D plane. By adding this, we say that we make it so that it intersects at infinity. Basically, it's just to make sure that the lines that do not meet somewhere or in infinity in a sense. It's two straight lines that eventually curve and meet at some arbitrary infinity points, not particularly regular space. Yeah, I think that's essentially what it's trying to say. The general From my understanding, at least, the general reason why we want this or we want to define there is a point at infinity and things intersect there is so that some calculations, especially in elliptic curve, if you've seen elliptic curve constructions, I don't know if there's a picture here. Yeah, so it looks like this. Some of the curves. Okay, this is a I don't like this curve. But anyways, so there the points here, they go to infinity, right? We to help us calculate, the points that might be calculated within like behind this point. We say that these lines will eventually meet in infinity by adding that extra, yeah, by doing this. Yeah, that's essentially it. It's very hard to visualize, I would say. Um, it's really hard to visualize this. But yeah, it's I guess to a certain extent it feels like 3D, but it's not really 3D. It intersects somewhere somehow. Um, yeah. Anyways, great. Yeah, I think that's essentially it. We have 10 more minutes. Any questions, anything specifically you want to do like a final discussion before we end this? I'm pretty happy because actually this session I see a lot of contributions specifically on um, cryptographic groups. Yeah, thank you very much, all of you, for participating. Yeah. So, any more questions? I will take the silence as a not really. Mm, okay. since there are no questions, I'm not gonna end this right now. Since there are no questions, and since we've progressed so fast across algebra, so the next section, actually the next week, I was thinking about covering elliptic curves, but let's do a little bit of exercise and let's make this slightly more interesting. So from our audience, um someone actually gave me a suggestion. So and which I will actually use. So one thing that I want all of you here to participate in is essentially there is a lot of things here, right? In chapter 4. I would like you you all um of course no pressure, but I would like you to implement groups, rings, and fields in whatever programming language you like. And this exercise is to basically help you. I mean, at least for me, this is something that will help me understand it more practically. And I'll open up a GitHub and allow you to basically push or submit PRs to the GitHub um, your implementation, right? And again, if you haven't joined the Telegram group yet, tell me. I'll share the link here, or I'll share the QR here. I'm assuming all of you here already are in the Telegram group. Yeah. But anyways, try to implement groups, rings, fields, in whatever programming language you choose, and try to make it so that yeah, wouldn't it just be mod p arithmetic? Yes, it will be. However, I want basically make it so that yeah, it's essentially exercise, right? But I would say, if possible, don't like so allow what you have implemented, like make your what you've implemented into a library, and what we'll do. So these are all quite simple stuff, yes. But what we want to do, or we will do, remember to also implement, by the way, parental extension as well. Try to implement this functionality. By the way, Sage does provide a lot of tools. If you can, don't use Sage, but if you want to, you can use Sage. It's basically Python. It runs Python script, by the way. If you do Sage and put Python script behind it, it actually executes it with all the libraries there. But if you can, try not to do that. Try to implement it from scratch by yourself. Um, Try to implement parental extension, projected planes as well. And the point, or like more like the idea is, with this implemented, we would like, or the goal is to that so the next time when we talk about elliptic curves, we can start implementing curves with what we've implemented here, right? We want to build on what we've implemented in chapter 4 and continue on. This is a little bit of experiment on my part, and also yeah, but yeah, if you yeah, please do that. Please try to implement gross ring fields, the extension, the planes, and any algorithm in middle, right? There's a lot of algorithm that they use to calculate where is it? There is the hashing, yes. Hashing into groups or hashing to fields. Try to implement those as well. Um yeah. So that's something, that's a little bit of homework. Um As for next week, what we're going to cover. So next week, I'm going to put it a little bit chill. So next week, we're going to take a look at some of the implementation, talk about what we've implemented for the first 10 to 20 minutes. And we'll cover the short Weierstrass curve. And I think we'll just cover the three curves. So the Weierstrass curves, the Montgomery curves, and the twisted Elliott curves. Not included in the homework is to implement this, but if you do implement them, it'll be great. So I mean, next week's homework essentially is to implement these three, right? But yeah, so I'll put it in the summary. Implement what you've learned in algebra, specifically groups, rings, fields, and the hashing, extension, projective planes, and look into this tree, study into this tree that we're going to go through next week. Only these three, so 5.1, 5.2, and 5.3. If you want to, you can implement them first. But next week we'll actually try to implement this. Yeah. So that's essentially it for this week. It's almost time. Any more questions before we end? Great. On one more note, I'll also hmm, I would like to open a Notion to actually let us put in our thoughts and discuss and put our notes there from what we've learned. That's also a very good suggestion from the group here. Yeah, so I'll share all that in the group again, like in the Telegram group again. So again, if you haven't joined yet, tell me. I'll share the link to you. Yeah, but I think that's it. Thank you very much once again for coming, and see you guys next week.